Bam! Mr. Tarot. In this video, we are going to learn how to recognize a homogeneous differential equation, and then we're going to do 3 examples, giving us some practice and experience of how to help you do your homework dealing with these kind of equations. In the description, you will find a link to my other video, solving first-order differential equations and solving separable differential equations. So now that we look at this third type, how are we going to recognize when we have a homogeneous differential equation, and what do we do to solve them? Well, you can manipulate, if you can manipulate the differential equation to have a dy dx, so first order differential equation, on one side, and then the other side of the equation to be some kind of function in the form of f of y over x. So like we have here, we have our first example, dy over dx is equal to x cubed plus y cubed, excuse me, over x times y squared. And you won't maybe necessarily know this right off the bat. There's lots of different types of differential equations, and it can become quite complicated knowing how to attack them. So it takes some experience and time with your homework and different types of these problems to get used to this. But if you can prove to yourself that it is a homogeneous first-order differential equation if you can manipulate it into that form of y over x. So we see here that we have on the right-hand side a term of x cubed. Well, that's certainly not in the form of some kind of y over x. So maybe I divide both the numerator and denominator by an x cubed so that this first term becomes a 1. Well, what else is going to happen? Well, our y cubed divided by x cubed is going to be, well, y cubed over x cubed. And then here we have x y squared divided by x cubed is going to yield y squared over x squared. Well, this can be rewritten, excuse me, as dy over dx is equal to 1 plus y over x cubed over y over x squared. And so here we see that we have, basically it's not one independent variable, but we have this form of f, the f of being 1 plus something cubed over something squared, and that expression being substituted into that function f is our y over x. So we have that y, or that f of y over x format. Now, as we do the examples, excuse the coughing please, I'm going to write them as we get started, all 3 of these examples in this form before we start the process of solving these homogeneous differential equations. But you can recognize them by when that differential equation is written in the form of f of x and y. So not y over x, but just within that function you have a combination of variables of x and y working together like we have here. All the terms on the right-hand side, so you're still wanting to isolate that dy over dx notation, all those terms on the right-hand side have the same degree. So we have x to the third, which has a degree of 3. We have plus y cubed, which has a degree of 3. And now in the denominator, we have x to the first times y squared. Well, this is one term. It's a product, of course, of some variable of x and y. And if you take those exponents of 1 and 2 and add them together, you get, again, a degree of 3. So one term, degree of 3, another term, a degree of 3, a third term in the denominator of this, well, actually one big, somewhat complicated term, which also has a degree of 3. So that's your indication that, hey, I think I'm looking at a homogeneous differential equation. Let's try and manipulate it into that form of dy over dx is equal to some function f of y over x. Now, if you can do that, we have the 2 steps, or actually a few steps, that we're going to take to solve these problems. We're going to substitute, we're going to take out that y over x expression and substitute in a new variable of v. So we're going to just say let v equal y over x. Well, if we let v equal y over x, then we can say, by multiplying both sides by v, that y is equal to vx. Now, why do we do that? Well, to start solving this homogeneous differential equation, we're going to remove all references of y. So we want to take the y's out and replace them and just rewrite this entire differential equation to be in terms of v and x. So we need some kind of substitution for dy dx. Multiply both sides by x, find dy over dx by using the product rule, the derivative of the first with respect to x times the second factor, then plus the first factor, v, times the derivative of x with respect to x, which is just equal to 1. So we have dy over dx is equal to dv dx times x plus v. Your book might also show this as dy, multiplied both sides by dx, and you might see that dy is equal to dv times x plus v times dx. Just need to be consistent with whatever book you're using. And then we're going to do two substitutions. We're going to take our dy dx out and replace it with dv dx, x plus v. And any place that we have a y over x expression, we're going to replace that with v. And that's going to transform this homogeneous differential equation, first order, into a separable differential equation. And we're going to learn, or not learn, but practice and reinforce those skills that we learned in just a couple of sections ago when we learned how to solve separable differential equation. So the first example coming up right now. So for our first example, let's just finish what we started. We have our differential equation. We have put it into the form of f of y over x. And now let's take that first step and let v equal y over x. Well, and that's going to give us one substitution, but now we're going to solve that for y. Find that dy over dx, just take the derivative of that product with respect to x, and again we have that dv over dx times x plus, so we took the derivative of the first factor and left the second alone. Now plus, we're going to leave the first factor alone and take the derivative of the second, so plus v. Now, you know you've done this, or you're in the process of doing this correctly, if you can remove all the references of y from this homogeneous differential equation and have it all in terms of x and v. So our dy over dx comes out, and we have dv over dx times x plus v, and then we have equals 1 plus v cubed over v squared. And we're looking to now separate the variables and finish solving this. So let's go ahead, and we have variables of v on both the left and the right hand side, so we're going to bring this over with subtraction. We have dv over dx, and my apologies for the air conditioner, but it's right outside the window, and it's Florida, and it's hot. So anyway, yeah, we're going to subtract both sides by v. We're going to need to do a little bit of work, of course, to find a common denominator. Multiply the top and bottom by v squared. And we have dv over dx times x is equal to, and of course we're going to have a v cubed here. So we have a common denominator, so 1 plus v cubed minus v cubed is going to be equal to 1 over v squared. We're going to separate these variables now. We're going to both at the same time divide both sides by x and multiply by dx, and then I'm going to multiply the v squared over to the left-hand side. So we have v squared dv is equal to, again, dividing both sides by x and moving the dx over with what looks like multiplication, and we have 1 over x dx. And now we have all our variables of v on the left-hand side, all our variables of x on the right. Of course, we have a dv and a dx indicating a derivative of x and a derivative of v. We're going to now integrate both sides of this equation. And remember, you only have to put the plus c on one side, so we're going to have the integral of v squared with respect to v is going to be 1/3 v cubed is not plus, but equal to the integral of 1 over x dx is the natural log of the absolute value, don't forget that, of x, and then our constant on just one side. It's not necessary to put it on both, because a constant and a constant, you bring it over with subtraction, you get another, constant. Well, that's practically done. Again, we didn't start with the most complicated problem here, but this solution, this general solution with the plus c, has a v in it. Well, our original differential equation did not have any references to v. We just used that as a tool to work our way through this process and transform our homogeneous differential equation into what effectively was then a separable differential equation. So we're going to get rid of this v, and we're going to plug in our y over x cubed is equal to the natural log of the absolute value of x. We're going to multiply both sides by 3, so we have y over x. And let's go ahead and raise that entire fraction to a power of 3. So we have y cubed over x cubed is equal to, multiplying both sides by 3, we have 3 times the natural log of the absolute value of x. And then, it's plus, really it's 3c, but a constant times 3 is just going to yield another constant. So you can just leave it as c. Your teacher might be writing like a c sub 1, c sub 2 maybe. You might have books now call this a instead of c, which is just another unknown constant. I'm going to leave it as another plus c. Multiplying now both sides by x cubed, and we have y cubed is equal to x cubed times 3 times the natural log of the absolute value of x plus c. And that's really, about as far as we can go. You might see this in slightly different formats. Maybe the 3 is up here as a power. Again, maybe that c is written as the natural log of c, and you have that combined. But that is the end of this first example. That is our general solution to this homogeneous differential equation, first order. Homogeneous differential equation, second example coming up right now. And for now, our second example. We have x squared times dy dx is equal to negative 2x squared plus y squared. And while we don't have the first derivative here isolated yet, I do see that each of my 3 terms has something involving a second degree. So it looks like we might be leading into that homogeneous differential equation situation. So we're going to divide each of these terms by an x squared. And hopefully when we're done, have a dy dx is equal to f of a y over x scenario. So we have dy over dx is equal to, here our x squared is going to cancel out, giving us that's equal to negative 2 plus, and then of course we have y squared divided by y squared, which we can write as y over x squared. So just in that one step of trying to isolate that derivative notation, we see that we already have a function basically negative 2 plus something squared, and that something being squared is that y over x. So now, like the directions said, we want to say let v equal to y over x, leading us to say that y is equal to vx, and dy over dx is equal to dv over dx times x plus v times 1. So again, we're just applying the product rule to that little equation there, y equals vx. To set up our 2 equations that we'll use, once again, for our 2 substitutions. That y over x is going to get replaced with v, and that dy over dx is going to get replaced with, well, this. dy dx comes out. We have dv over dx is times x plus v is equal to negative 2 plus, well now instead of y over x, v squared. But here, with that idea of separating the variables, we're going to move this term of plus v over to the right-hand side, and we have dv dx times x is equal to what? V squared minus v minus 2. Okay, so we're going to take this entire grouping here on the right-hand side of v squared minus v minus 2 and divide that to both sides of the equation. We're going to divide both sides of x to the left and the right, and we're also going to bring this dx over to the right. We're separating those variables of v and x. So we have 1 over v squared minus v minus 2 dv is equal to 1 over x dx. Now, of course, we know that once you separate those variables in a differential equation, the next step is going to integrate both sides of that. And we have a pretty easy situation over here on the right. The integral of 1 over x dx is just going to be, as we know, the natural log of x, and then your plus c for your constant of integration. But the left-hand side that we have here, well, of course, when you integrate a fraction, it's usually going to be some kind of u prime over u, as we have on the right-hand side. If it doesn't fit that u prime over u, your integrand, then maybe you're going to get an answer that involves an inverse trig function. And the problem that inspired me to write this one for our video notes, it had a constant here at the end of this quadratic that made it such that this was not factorable. And I'm thinking of this problem that we then took the first two terms in the denominator, went through the completing the square process to get something like maybe like a 1 over, and it doesn't have to be necessarily 1, but a 1 over a sum of squares, and leading us down to a path that has an answer involving some type of arctangent. So you'll probably have something like that in your homework. But here, we're going to review a different concept. We have 1 over, and we're trying to integrate 1 over v squared minus v minus 2, and this does not fit a u prime over u, and we're not actually going to have to go into some kind of completing the square process and leading to an answer that involves an inverse trig function, because our denominator here is actually factorable. This is equal to 1 over v minus 2 times v plus 1. Well, we just got done probably, well, my students did, you probably have been working with a little bit of integration involving partial fractions. So let's see if we can't come up with a couple of fractions that add to this single fraction of 1 over v minus 2 times v plus 1. Involving this, so in the description you'll find a link to 2, and it's got more than just 2 settings, but 2 full-length lessons for partial fractions, and it has some more involved situations, like maybe one of the factors repeat, we have some different degrees, maybe a higher degree in the denominator or something like that. But here this is a pretty easy scenario. We have a factor which is v minus 2, and we're looking for some kind of numerator that has a degree less than the degree of the denominator by 1. So this has a degree of 1, so we're going to look for a numerator that has a degree of 0, or in other words, a constant, and then that's going to be adding to a b, another unknown constant, over this other factor in our denominator of v plus 1. So we want a constant of a and b such that when you go to find, and you go through that common denominator process to add these two fractions, it just adds up to be, finally, an answer of 1. And because this is, in this type of problem, a simpler scenario, what we can do is a shortcut process that I learned through the last couple years of teaching that was not included in the pre-calculus book that I initially made my partial fractions videos from, where we're going to just take a v minus 2 times v plus 1 and multiply that factor through each of these three terms, basically just writing a new equation with no fractions. Of course, here our v minus 2 times v plus 1 cancel, and we have 1 is equal to, going to the first term on the left, on the right-hand side, the v minus 2 is going to cancel out, and we have a times what? X plus 1, and then this v minus 2 times v plus 1 getting multiplied to our last term here in the equation, we have plus b, and with the x plus 1 canceling out, we have, oh, I wrote x, v minus 2. Okay, so this shortcut thing that I thought was really cool with some of these more straightforward scenarios here with partial fractions, this needs to act as an identity. This needs to be true whether, regardless of what value v takes on. Now this is a little bit disconcerting, a little bit weird, because I'm going to pick values that actually make these terms up in the previous line of this work undefined, but it does work out nicely when this is a possibility. I want to come up with and let v equal some value that's going to allow one of these terms to disappear, and if I can make that happen and easily solve for the other variable, well, then I'm good to go. So we're going to say let v equal negative 1. Well, if I do that, we have 1 is equal to, of course, negative 1 plus 1 is 0, so we have negative 1 minus, well, I'll write this out, b times negative 1 minus 2, which is going to give us 1 is equal to 3b. Therefore, b is equal to negative 1/3. Now let's do this again, but with a value of v that allows the b to cancel out in this equation. So we're going to let v equal 2, and that's going to give us 1, because there's no v here in this term, is equal to 2 plus 1, which is 3, so 3a. Of course, 2 minus 2 is 0, so the b is going to cancel out of this identity. If we're going to act like this is an identity, we have a is equal to actually 1/3. In this particular case, the constants are the same value but opposites. That does not always happen. We have here that 1 over v minus 2 times v plus 1 is equal to that constant of a. Now, instead of writing it a over v minus 2, I'm going to write the a as a 1/3 off to the side, and then multiply that by 1 over, just a little bit cleaner way of seeing how you get the 1/3 over v minus 2 to equal what it should be in simplified form. So we have a times the 1 over v minus 2, and then plus b, but b is negative, so minus b, or minus the 1/3, which is the b, plus b, times 1 over v plus 1. So this means that we're going to take out, or our next line here after I clean all this up, the integral of 1 over v squared minus v minus 2 dv is going to be the integral of 1/3 times 1 over v minus 2 minus 1/3 times 1 over v plus 1. Now, really not necessary, but just to kind of like make sure my notes are very small, has very small incremental steps and you completely understand this, I'm going to give each of these terms their own dv notation and pull the 1/3. Actually, now let's do this. Let's bring the 1/3 out of each of these. And we're going to go ahead and integrate each of these terms, or maybe I could have written that original 1/3 times the definite integral of 1 over v minus 2 dv minus 1/3 times the indefinite integral of 1 over v plus 1 dv. But regardless, we're going to have here 1/3, the integral. Now, if we see the u as thinking like that u prime over u pattern, we have a denominator of v minus 2. The derivative of v minus 2 with respect to v is just 1, and the derivative of v plus 1, of course, is 1. So we do have that u prime over u pattern. So we're going to have 1/3 times the natural log of the absolute value. Here are integrating, again, u prime over u is going to be the natural log of the absolute value of v minus 2, and then minus the natural log of the absolute value of v plus 1, with that 1/3 out front. And the integral of course, 1 over x dx is the natural log of the absolute value of x plus c. Okay, so a couple of things I want to do here. I'm going to go ahead and multiply both sides of this equation by 3 just to get rid of that coefficient of 1/3. And we do have the natural log, two natural logs subtracted. Well, natural logs give you exponents, right? And when do you subtract exponents? Of course, we are in calculus. I don't know why I always feel like I can just stop and make sure you remember this, but you can't stop the video and ask me questions and have me respond. The natural log of a minus the natural log of b, of course, is the natural log of a divided by b. You subtract exponents when you divide with a like base, and of course that like base is the base e of natural log, or log base e. So the natural log of the absolute value of v minus 2 over v plus 1 is equal to 3 times the natural log of the absolute value of x, and then plus, now multiply the left-hand side by 3, that cancels out with the 1/3. The natural log of x times 3 is 3 times the natural log of x. 3 times a constant just yields another constant. You could argue that, maybe it's c sub 1, c sub 2, or something like that, or sometimes math books now will change it to an a, but it is just another unknown constant, so I'm just going to leave it as c. Two things. We still have natural logs, and because you have a natural log on both sides, so we're going to go ahead and make sure that we clean this up by getting rid of that, and we need to get rid of the reference of v. So because we're kind of getting into that general solution to our homogeneous differential equation, but that is in terms of x and y, not x and v. So first we're going to bring this 3 up and bring it up using the power rule of logarithms and say that we have the natural log of the absolute value of x cubed, which is equivalent to the absolute value of x and then cubed. But we can bring that inside the absolute value notation. That's going to allow us then to make both sides of this equation an exponent of e, and that plus c is part of the exponent of e. Okay, well, the e, which is an exponential function, and logarithms, which are an inverse math operation to exponential functions, or that log base e, will cancel out. So we have v minus 2 over v plus 1 is equal to, and over here we have a sum of exponents on top of a base. Well, when do you add exponents? When you're multiplying like bases. So this e to the natural log of the absolute value of x cubed plus c can be written as e to the c times e to the natural log of the absolute value of x cubed. Well, e is a constant. Raised to a constant is another constant. And here we have the base e and the natural log. Again, these inverse math operations, they're going to go ahead and cancel each other out, leading us to say that we have v minus 2 over v plus 1 is equal to e to the c, which is another constant, times, and then the base c and the natural log cancel out again, and we have c times x cubed. Now, we need to get rid of the reference to v. Now, what was v? V, of course, is equal to y over x. So now we have taken out the v's, y over x minus 2 over y minus y divided by x plus 1. That's probably must have been on the previous line. Equals c times x cubed. Multiply both the numerator and denominator of this pretty complex fraction on the left-hand side by x. To just kind of clean this up a little bit. And our final answer is going to be that, of course, x times y over x is going to be equal to y. X times negative 2 is negative 2x. Our denominator here, we have, again, those x's canceling out, so we have y plus x is equal to c times x cubed. Okay. Now, one thing I just want to add to this problem before we go on. There are times when we have this base c and this natural log cancel out, and this is something I do struggle with, even though I've been teaching for a lot of years, and maybe somebody can give me some feedback here. You know, sometimes we can justify how we drop these absolute value symbols, like if this inside expression was an x squared plus 4, which is never going to be negative, then even within this line here, and also after you cancel the base c and the natural log, you don't need to justify how those absolute value symbols sometimes just sort of disappear, and then maybe sometimes they actually stay within the problem. In this section of where I'm teaching from, they just pretty much consistently allow these, when the base c and the natural log cancel out, to allow those absolute value symbols just kind of fall away. Honestly, that still kind of bugs me a little bit, but I am being consistent with the solutions that I'm seeing from my book, and like saying, this isn't really an AP calculus style question, it's beyond that, but a lot of times, like on AP calculus, they allow just those absolute values in this step to just fall away sometimes and not really require you to justify, you know, sort of like where they're going. So it's a little bit of a weird thing here I have with this particular problem, but it is what it is. For now, let's get on to example number 3. Now, it will probably make my YouTube video a little bit long and hopefully not turn off too many people looking for help, but we're going to do this 2 different ways. I'm including this example. It's not really terribly unique and actually fairly similar to our last example, but this particular problem, if you look at it long enough, you may recognize, hey, wait a minute, why are you doing it this way? I could have done it, you know, basically another way. This can be worked with in terms of recognizing that it's a homogeneous differential equation, but you might also recognize that somewhere in there is a first order, the first order linear differential equation that you can, you know, transform into exact form, which I'll review with you in the close of this video. So, but you're in the section of homogeneous differential equations, there where you probably just got that fresh new tool in your head, and that's what you're just focusing on. So we're going to go ahead and get this solved for dy dx by dividing both sides by 2x. Here for the first term, the x is going to cancel out, giving us just a 1/2, and then minus 1/2 with a negative 1/2 times y over x. Voila! We have a first order derivative, and in the form of f of 1/2 minus 1/2 of something, and that something is our y over x. So again, let v be y over x, y is vx, and therefore dy over dx is dv dx times x plus v. Do our substitution, and we have dv over dx times x plus v is equal to 1/2 minus 1/2 of v. Separating the variables, we're going to go ahead and bring this v over with subtraction and have dv dx times x is equal to 1/2, and then minus 1/2 v minus v. Of course, this needs to have a common denominator, so we have 2 over 2v, and we're looking at dv dx times x is equal to 1/2 minus 3/2 v. Not x, but v. Let's try that again. Okay, well, that's fine, but it's going to be a little bit cleaner to write this as 1 minus 3v over 2, that common denominator. And now we can see that we can bring this x over with division, the dx bring it over with what basically looks like multiplication, and divide both sides by our 1 minus 3v, giving us 1 over 1 minus 3v dv is equal to, remember we have a division of 2 here, and we're going to divide both sides by x, so we have a 1 over 2x dx. And we've got the variables separated. We're going to solve by integrating both sides of this equation and recognizing that this is sort of like thinking about our integration rules. A lot of times with fractions we can make a u prime over u pattern, and if our u is negative 1, 3v, then u prime is going to be just negative 3. So we need our numerator to be negative 3. I'm going to introduce a multiplication of negative 3 in the numerator. So we have that u prime over u pattern, and of course balance that with a division of negative 3. So we have negative 1/3 times the indefinite integral of negative 3 over 1 minus 3v dv. And here we're just going to move the 1/2 out front. 1/2 times the indefinite integral, and this 1 over x dx keeps showing up in my examples. Hopefully it's not becoming too repetitive. And we have negative 1/3. This is u prime over u, so we have negative 1/3 natural log of the absolute value of 1 minus 3v, and that is equal to 1/2 times the natural log of the absolute value of x plus c. Now, I have a coefficient. We're going to use that same get rid of the natural logs by making both sides of this equation an exponent of base e, but I don't really want to work with a square root and a third root at the same time. So I'm going to go ahead and multiply both sides of this equation by 2. So we have negative 2/3 times the natural log of the absolute value of 1 minus 3v is equal to the natural log of the absolute value of x plus c. We're going to bring this negative 2/3 up as a power. Natural log of the absolute value of 1 minus 3v raised to the negative 2/3 power. Actually, we can bring that on the inside too. Let's go ahead and do that. And now we're going to go ahead and make both sides of this an exponent of e to cancel out those natural logs. And here, it's a little bit easier to say, well, when the space c and the natural log cancel out, do we still need those absolute values? Can we justify that it's going to go away? Well, with this negative 2/3 coming up as a power, taking the third root of something can yield a negative number, but then raising it to an even power then is going to guarantee that it's positive. So now here it's kind of like a little bit better to easily justify why you're just letting the absolute values drop away, even though they kind of seem to arbitrarily just drop away in my, say, AP Calc classes I teach, and where you don't have to justify it. It does bother me, and maybe if you've got some insight with a little bit more understanding of these problems and just deeper understanding mathematically, or you've had your teacher or textbook explain this, I would appreciate a little bit of help in the comments below. But at any rate, we're going to have this space c and the natural log cancel out, giving us with 1 minus 3v. I've often said that teaching on YouTube and not just my classroom has made me a better teacher, because sometimes I get help from you all that is more insightful than what I get in my textbooks or what I remember from my college years, 25 years ago, or even from my students in class, because just, huge array of intelligent people watching my videos. Thank you very much. So this is going to be e squared, or raised to the c power, because of course again we have those sum of exponents with our base of e, and then so we have e to the c raised to, or times, not raised, but times e to the natural log of the absolute value of x. So the e to the c is going to give us just another constant, which you might call now a, or another c, and here the base c and natural log cancel out, so we have c times the absolute value of x. And we have our 1 minus 3v to the negative 2/3 power. Okay, so we need to get this in reference to v's and x's. So we have our 1 minus 3 times y over x. And I'm starting to run out of space, and I'm pausing because I want to get this one set equal to y. So that means that we're going to want to get rid of this power of negative 2/3, and I'm running out of space. What I want to do here is I want to, with the goal of getting this y equals, which we often like to do when solving differential equations, but sometimes we'll get away with not doing that. We're going to get rid of this power of negative 2/3 by raising both sides of this equation by a power of negative 3/2. And so again here, if we're going to take the root of some number, it's going to have to be positive. So I'm going to let that x drop away, or the absolute value, because it's, again, just sort of like you can't take an even root unless this is a positive value anyway. The constant raised to another power is just another constant. So we have c times x to the negative 3/2 power. Now we can subtract both sides by 1. Divide both sides by negative 3. C divided by negative 3 is another constant. Negative 1 divided by negative 3 is positive 1/3. And now multiply both sides by x, and we have y is equal to, now if we multiply both sides by x to get rid of this division of x, of course here the y over x times x is going to cancel, and x to the negative 3/2 times x to the positive 1, or 2 over 2, is going to be x to the negative, so c times x to the negative 1/2 power plus 1/3 x. And yeah, so I can write this as, oops, did I miss a negative somewhere? Well, yes or no, I'm going to point this out when we take a look at the second way of looking at this problem. That's also another reason why I'm doing this both ways. You may, the c divided by negative 3, mark that as a negative constant because you've taken a constant and divided by a negative number. We're going to show with the finding this answer another way that plus or minus, having a plus or minus in front of an unknown constant is not really important because you don't know what the constant is. And so is that, positive or negative, and how does that affect the negative that's there? So we have y is equal to basically like a negative c over the square root of x, or negative c times x to the negative 1/2 power. plus 1/3 x, and that does match my notes. Okay, now, what if we were to see this problem another way? So, we had that original problem, we worked it into dy dx, see that y over x pattern, recognize that it's a homogeneous, first order homogeneous differential equation, use the substitution to get rid of dy dx and to get y over x in terms of v. Should probably have those little substitution formulas left up there at the top. But now when you look at it in this form, you might see this in a different light on, how to solve it. The directions said that after these two substitutions that you would create a separable differential equation. But if, which is not untrue, we just worked it that way. Where did I put my chalk? But if I add a 1/2 v to the other side, both to the right and left-hand side, well then 1 plus 1/2 is going to yield dv over dx times x plus 3 over 2v is equal to 1/2. Okay, so now we're going to isolate this dv over dx by dividing each of these terms by x, or multiplying through the entire equation 1 over x, and that's going to give us x divided by x, of course, is 1, so we have dv over dx plus 3 over 2x times v is equal to 1 over 2x. This is in the form of a first order linear. This is a v to the first power, a first order linear differential equation, where this is our p of x function and this is our q of x function. So if you're just looking at this type of problem, maybe later on after studying multiple forms of differential equations, so you're not looking at just like this one most recent tool, you can manipulate this not into a separable differential equation, but recognize that it is also can be written as a first order linear differential equation. And if you do that, then of course hopefully we remember how to find that integrating factor. Like basically, how do you come up with a factor so that you can multiply it to both sides of this linear differential equation to get it into exact form, where the left-hand side is the result of the derivative of a product. What can you multiply to both sides of this equation? So the left-hand side result is basically the result of a derivative from working through the product rule. Well, our integrating factor is equal to e raised to the indefinite integral of our p of x function. So our integrating factor is going to be e raised to the indefinite integral of what? 3 over 2x dx, which means that we're looking at our integrating factor is e raised to the 3/2 times the natural log of the absolute value of x. And with coming up with the integrating factor, we always assume that c is equal to 0. So if we bring this 3/2 up as a power and let the base e and natural log cancel out, we have that our integrating factor is just x to the 3/2 power. And we don't need, again, the absolute value, because if you're going to indicate that you're taking a root, that implies that your base has to be positive anyway, so the absolute values are a bit redundant. So now we're going to take x to the 3/2 power and multiply that through each of these three terms of our differential equation, and we have x to the 3/2 power times dv dx plus, now plus what? We have 3/2, 3 over 2, and this is x to the negative 1 times x to the, what, 3/2. And negative 1 plus 3/2 is going to be x to the 1/2, right? X to the 3 over 2. I should probably just be writing this instead of talking through it, but I'm going to run out of space. So when you take this x to the 3/2 power and multiply it to the second term, you're going to have x to the 3/2 power over x to the first. Of course, we can subtract those exponents. And v, right, don't forget the v there, is equal to, again, here we have 1/2, or 1 over 2 times x to the first. Well, now you're going to multiply that by, well, I could write it here. You're going to divide like base as you subtract those exponents. So once again, 3/2 minus 1 is 1/2. Okay, so do you see what we have here? If you just recently did this section in your textbook, we have x to the 3/2, and the derivative of x to the 3/2 is 3/2 x, and you reduce that power by 1, x to the 1/2. And here we have a factor of v, and in the first term we have a factor of dv. So this is like, what? P times, what? Q prime plus P prime times Q. The left-hand side is the result of taking a derivative of the product of two factors. So the left-hand side can be written as, and this is a derivative with respect to x, the derivative with respect to x of x to the 3/2 power times v. And the right-hand side is just 1/2 x to the 1/2. And someone's coming home. Okay, we're almost done. If you've made it all this far, thank you so very much for watching all the way through this video. I hope it has helped. I'm going to go ahead and just for notation's sake, I think it's cleaner. We're going to move that dx over to the other side, and we are almost done. Now, we got a derivative of the left-hand side. We have, of course, terms of x and v. We actually, we're going to take the integral and just let that cancel out. We're going to integrate both sides of this equation, and that integral and derivative process, of course, just cancel out. Our left-hand side is just going to be x to the 3/2 times v, which we knew already. We set that up, making the left-hand side the result of the product rule, derivative resulting or using the product rule. The right-hand side, we're going to raise that power by 1 and then divide. 1/2 plus 1 is, what, 3/2. Divide by that or multiply by the reciprocal, and we have 1/2 times 2 over 3. And don't forget that constant of integration. The division of 2 and multiplication of 2 cancel out. And we're going to go ahead and take that v out and replace it with y over x, right? We don't want our final answer to be in terms of v when it wasn't part of the original problem. So we have x to the 3/2 power times y over x is equal to 1/3 x to the 3/2 power plus c. X to the 3/2, again, divided by x to the first, is going to be x to the 1/2 power times y is equal to 1/3 x to the 3/2 plus c. And now dividing, chalk down! And now dividing everything by the square root of x, or having that x to the negative 1/2 power like we had in the other version of our answer, we have y is equal to 1/3 x plus c divided by the square root of x. Now, what do we have in our other answer? We had y was equal to a 1/3 x, and it was minus c over the square root of x. But again, plus or minus an unknown constant, we don't really know the sign of that unknown constant. So the plus or minus here isn't really important. So here we have a problem that once we recognize that it was a homogeneous, first order homogeneous differential equation, we could go through that separation of variable process. But actually this one is a little bit shorter if you could have seen that developing first order linear differential equation. But either way, we got the same answer, and I hope you made it to the end. I hope this all helps. I miss it true. Bam! Go do your homework. Fell right into that dy dx is equal to f of y over x. And let's see what my little doggy is barking about. This is our excellent watchdog Dory, and hopefully with a little bit of distraction, she'll stop distracting us. Okay.